Hi and welcome to this junior cycle higher level maths video where we're looking at probability. So we're going to focus on some of the main topics from the probability section, which include listing outcomes, probability scale, calculating probabilities, multiple events, so using the and or, two-way tables, probability tree diagrams, expected frequency, and then relative frequency, which is also known as experimental probability. In the second video, which is linked in the description below, we're going deeper, looking at more problem-solving questions that can come up on the higher level paper, and we're going to look at how to work with sets.
So let's talk about two words we're going to meet again and again. They are outcomes and events. So these two words appear in most questions, but many students struggle to understand, well, what exactly does that mean? So let's be very clear at the start and define these. So an outcome is a possible result of an experiment. So for example, when you roll a die, what can happen? What are the outcomes? And they are, you can get a 1, a 2, a 3, a 4, a 5, or a 6. And that is it. That's all that can happen when you roll a die. An event is one or more outcomes of an experiment. When we're working in probability, we're usually asked to get the probability of an event. So for example, getting a tail when tossing a coin, rolling a 7 with 2 dice. So an event can include one or more possible outcomes. So for example, choosing a king from a deck of cards, that is an event, but it actually has multiple outcomes because when I choose from a deck of cards, there are actually 4 different kings that exist in that deck of cards. If you're not familiar with deck of cards, don't worry, we are going to do a little bit more on it throughout the video. Let's look at an exam question, and this is from the old junior certificate papers, and it's asking us to match the description to the terms. So our 3 terms are outcome, which we've met, sample space, which we haven't met yet, but we will meet later in the video, and event. We've met event as well, so by process of elimination, if we can figure out the correct description for outcome and event, the third one will have to be sample space. So the descriptions are the set of all the possible outcomes of an experiment, one possible result of an experiment, or a subset of the sample space, a collection of one or more outcomes. So we know that an outcome is a possible result of an experiment. So let's add that in. So there is my outcome there. An event was a collection or a set of one or more of the outcomes. So that was our last piece in here, meaning a sample space is the set of all possible outcomes of an experiment. So like I said, we're going to meet a little bit more about sample space later on in our video. So let's talk about the fundamental principle of counting. So this firstly probably sounds very complicated, but I promise that it's not. It's a very, very simple idea, but it's also a very important idea that will help us as we move through this whole probability section. So when there are m ways of doing one thing and n ways of doing another, there are m times n ways of doing both. So let's look at an example to make sense of that. Here I have some clothing options, and if I have 3 shirts in 3 different colors, so we see our red, our yellow and our green, I have 2 either belt or no belt, so that's 2 options there with regard to my belt, and I have 2 sets of pants, so I have my blue jeans and I have a brown pants. So how many different outfits can I make? So using the fundamental principle of counting, that would simply be 3 shirts multiplied by 2, either belt or no belt, multiplied by 2, meaning I would have 12 outfits. So for example, I could put my blue jeans with a belt and a red shirt. I could do the blue jeans, the belt with the yellow shirt, and the blue jeans, the belt and the green shirt. And if I kept going looking at all my different outfits, there would be 12. So this simplifies down to, if I want to work with, I suppose, here we have multiple things happening, and we want that word and, A-N-D, to represent a multiplication in maths. So think of it like this. I have 3 shirts and 2 belt options and 2 pants options. So that and will be multiplication. And that's really what the fundamental principle of counting is about. So let's look at an exam question that examines the fundamental principle of counting. So here's a menu from a restaurant. There's a 3-course dinner, so starter, main course, and dessert. How many different 3-course meals could be ordered? So we could start trying to write them all down, but it will take quite a while. So instead, let's break this down using the fundamental principle of counting. We have 4 starters and multiply. We have 5 main courses and multiply 3 desserts. Now you can work this whatever way you want. So 4 times 5 is 20, 20 times 3 is 60. So there are 60 different 3-course dinners that can be ordered from the menu. Now let's talk about probability scale. So probability scale is something you've probably met before. It is like a number line that goes between 0 and 1. So that's really important. The probability, if we're getting an answer, must be between 0 and 1. Now probability, and we'll discuss this in more detail, but it can be written as a decimal, it can be written as a fraction, or it can be written as a percentage. So the word we use that means fraction, decimal, or percentage is proportion. So if you want to think of it as that, that's absolutely perfect. The probability scale, as well as being a number line, can also indicate to us what the likelihood would be of something happening. So for example, we have impossible, which is a probability of 0, unlikely, which is down in like the bottom half of our number line, even chance, so that's dead in the middle. So think of that as you're tossing a coin, so half heads, half tails, 50-50. You think of it as probability of a half, 0.5. We have likely, which is in the top half of our number line, and then certain, which is a probability of 1.
One thing that's very easy to get confused about when we're dealing with probability is questions related to the idea of likelihood and questions related to probability. So when you're asked for likelihood, what we're being asked for is what we've just looked at on the probability scale. The answer should be a word like likely, impossible, even, and so on. However, if you're asked for probability, what they want us to do is to give a number answer between 0 and 1. And that answer can be as a decimal, it can be as a percentage, or it can be as a fraction.
So when I'm working with probabilities, we are going to think of it as the number of ways it can happen over the number of possible outcomes. So let's do something quite visual here. When a coin is tossed, there are 2 equally likely outcomes. And we say that the probability of getting tails is 1 in 2, or a half, or 0.5, or 50%. P bracket just means the probability of. So when we have P bracket tails, that's us saying the probability of tails is a half, or 0.5, or 50%. We generally give our answers as probability unless we're told in a question to do it in a different way. So Tony tosses a coin. What is the probability of getting heads? So if we toss a coin, I'm going to use an English coin here because it helps us understand the heads and tails just that little bit better than the euro coin. So we have a heads that we could get, looks like this, over the total number of possible outcomes. Well, if you think of when you toss a coin, what can happen, and it means you can get heads or you can get tails. So we have one answer we want, so getting the heads, over 2 possible things that could happen. So a 1 in 2 chance. Now that's quite instinctive, and most students will have that kind of without thinking too deeply about it. However, it's important we understand how to calculate probability and how to work this before the questions get more challenging. So let's talk about a die. So Amy rolls a fair die. What's the probability of getting a 4? Now, a very common wrong answer here is 4 and 6. So be careful, it is not 4 and 6. Let's figure this through. So how many different ways can it happen? Well, how many 4s appear on a die? And the answer is there's only one. It's there. And then, well, what are all the possible outcomes that we could get when we roll a die? And we could get a 1, a 2, a 3, a 4, a 5, or a 6. So the probability of getting a 4 when we roll a fair die is 1, the outcome we want, over 6 possible outcomes that can happen. So in the last example, I said that we had Amy had a fair die. So what do we mean by that word fair and its opposite, which is biased? So when we're talking about something like a die, we mean that all outcomes are equally likely. So everything has the same chance of happening. If we have something that's biased, so if we had a biased die, it means that it's more likely to land on some numbers compared to others. So you might have heard of like a loaded die, which is one that has a weight placed in it so that it rolls onto some numbers more often than others. So bias might also be a word that you've met in history where you're talking about maybe it being more one-sided or unfair. So think of biased as that opposite to fair. And when they tell us in a question that it is a fair die or that the system was fair, it just means that all outcomes are equally likely. And that won't always be the case because sometimes we think a probability, if we have 3 outcomes, then you have a 1 in 3 chance of any outcome, but that's not always going to be the case. And again, we're going to explore that further in the video. So let's look at an old junior certificate question from 2012. A, B, C, D, and E represent probabilities of certain events occurring. Write the probability of each event listed in the table below, and then part B asks us to place them on the correct position of the probability scale. Okay, so a club is selected at random from a pack of playing cards. So there are 4 suits in every pack of cards. So this is going to be a 1 in 4, or if it makes it easier for the number line, we could write that as 0.25. A tossed fair coin, there's our word fair again, shows a tail on landing. So that's a 1 in 2 chance, so 0.5. The sun will rise in the east tomorrow. So the sun always rises in the east and sets in the west. So that is a 1. That is a certain. May will follow directly after June. So the probability of that happening is a 0. May actually comes before June, so it is impossible for that to happen. And a randomly selected person was born on a Thursday. So think about this. Now, I suppose we could get deeper into it, but this question is saying that there are 7 days in a week and there's kind of an equal chance of being born on each. So we're going to say that this is 1 in 7. Now, if this was a printed question, we'd want to get our ruler out and make sure that we mark this accordingly, just like we would mark any number line. So I'm going to try eyeball it here. So there is my 0.5. Let me write my 0.5 underneath. And that is actually event B. And then halfway down here is clubs. So that is my event A, 0.25. The sun will rise in the east. That's there. It's certain. And May will follow June. Oh, so that's 0. Sorry, I meant to put a D here. So then we have one part left, which is about a randomly selected person born on a Thursday. So it might make a little bit of sense for us to think of a 7th in terms of decimal, just for placement, and that is 0.14. So it's kind of about just over halfway there, and this will be E. Now again, if I had this as a printout in front of me, what I would do is I'd use my ruler to divide it into 7 equal pieces so I could see where 1/7 was. because it does say the correct position, so I would try to do that as accurately as possible.
So let's take a look at question 5 from the 2023 Junior Cycle Higher Level paper. Part A tells us that the table below shows the outcome when the numbers A and B are multiplied together, where A and B are elements of n, so they're natural numbers, positive whole numbers. Write odd or even in each of the boxes to complete each of the mathematical statements correctly. The first one is done for you. So when you multiply two even numbers together, you'll get an even answer. So you can check this by taking any two even numbers and multiplying them together. For example, if you multiply 4 by 6, we get 24. It will work no matter what two even numbers you pick. The reason it works is that any even number has a factor of 2. Once you multiply an even number by another even number, we now have two factors of 2. So it will always be an even answer. What happens when you multiply two odd numbers together? So you can try by taking any two odd numbers and multiplying them. But what you're going to find is when you multiply two odd numbers together, the answer will always be odd. And the reason for this is because neither of those numbers have a factor of 2. So when you multiply them together, we don't get a factor of 2, so it can't be even. If you multiply odd by even, or if we reverse that and do even by odd, what we always get is an even number. And the reason we always get even is because this number here will be 2 by something. So when you multiply those together, your answer is going to have a factor of 2, which is the definition of an even number. So the reason we're doing this in a probability video is because the next part is getting into some probability, but looking at it in a slightly different way. So Rory rolls a regular, unbiased, six-sided die 3 times. He writes down the number on each roll of the die. Complete the sample space below, showing the different possible combinations of odd numbers and even numbers that Rory could roll. 2 possible outcomes have been filled in for you. So he could get even, even, odd, even. Sorry, even, odd. I'm going to do even, odd, even, or odd, even, even. Or you could have even, odd, odd. Or you could have odd, odd, even. Or odd, even, odd. Or odd, odd, odd. Take your time with this. Make sure you don't double count any outcomes. Try find a very straightforward way for you to work that makes sense. So then part C says each outcome in the table is equally likely. Rory multiplies together the 3 numbers he rolls. Find the probability that Rory will get an even number in his answer. So we're going to use what we did in part A to figure out which of these will give an even answer. So 3 even numbers together will give us an even answer. Even by odd will always give us an even answer. What we're looking for is any time an even number is multiplied in, it doesn't matter how many numbers you're multiplying, if one of them is even, our result has to be even, because as soon as you multiply by an even number, you're including that factor of 2, so our answer is going to have a factor of 2. It's going to be even, meaning that all of these will give us an even answer. And you can try it out with some random numbers if you want to double check, but the only one that won't give an even answer is where you're multiplying only odds together. What that means is we have how many outcomes? So that's 7 out of a total number of outcomes, that's 8.
So let's talk about multiple events. So this is where we're being asked for probabilities of multiple events happening. So if we have a situation where we're talking about multiple events, we try to break it down using the words and or the word or. If you can do that, you have a lovely little shortcut. So and means multiply. And we've met this earlier when we talk about that fundamental principle of counting. And the word or means add. So let's take a look at how that could appear. So I toss a coin twice. So there's our multiple event. So we're tossing a coin twice. What's the probability I get 2 tails? So what's the probability that I get tails and the probability that I get tails? So we can break this down into an and statement. So this is going to be the probability, so P, that I get tails and the probability that I get tails. So if we think about, well, what's the probability of getting tails when I toss a coin? That's 1 in 2. And means multiply, and again 1 in 2. Multiplying fractions, we multiply across the top. 1 by 1 is 1, and across the bottom 2 by 2, which gives me 4. So that's a 1 in 4 chance of getting 2 tails. So another example would be I roll a die. What is the probability that I roll an even number? So we can break this down into an OR statement. Now I know we could also work this, well, how many even numbers are there out of the whole die? But let's use this word and see if we can get the same answer. So the probability that I roll an even number is the probability that I roll a 2, or I could roll a 4, or I could roll a 6. So that word or means add. So the probability of getting a 2, I have a 1 in 6 chance of that happening. Or, so plus a 4, which again is a 1 in 6 chance, or, which is a plus a 1 in 6 chance of getting a 6. They are all over 6, so I have 1 6 plus 1 6 plus 1 6. That gives me 3 over 6, or simplifies that to a half. So we get the exact same answer as if I were working on this question as even numbers over the total number of numbers, but we've broken it down using our OR statement. So let's look at an exam question from the junior certificate paper. A fair circular spinner consists of 3 equal sectors. 2 are coloured blue, 1 is coloured red. So here's my red, and here is blue and blue. So what's the probability of the spinner landing on a blue sector? Well, there's 2 blue out of 3 sectors in total, so a 2 in 3 chance. Find the probability of getting a head and a red. So let's get the probability of a head when we toss the coins. That's 1 in 2. And, which means multiply, getting red. So the probability of red on this spinner, so that's a 1 in 3 chance. When we multiply our fractions, we multiply across the top. So 1 by 1 is 1, and across the bottom, 2 by 3 is 6. So I have a 1 in 6 chance of that happening. So find the probability of getting a tail and blue. So the probability of getting a tail is 1 in 2, and the probability of getting blue, so that's multiply 2 over 3, multiply across the top, across the bottom, we get 2 over 6, which can be simplified to 1 over 3. So now let's explore 2 events in a little bit more detail. So when we toss 2 coins, what are all the possible outcomes? So we've already discussed how to use and in order to calculate probabilities, but here we're asked about all the possible outcomes. So there isn't a shortcut, we just need to figure out what happens. So here's what could have happened. We could have got heads and heads, so HH, heads and then tails, HT, tails and then heads, and then tails and tails. And yes, heads and tails and tails and heads are actually different because you're tossing 2 coins. So if you think of the first letter as the answer from coin 1 and the second letter as the answer from coin 2, you can see that actually HT is different from TH. So as there are only 2 outcomes for each event, the total number of outcomes for both events is going to be 2 multiplied by 2 equals 4. And where that comes from is the fundamental principle of counting. So the first coin, there's 2 options. And on the second coin, there are 2 options. So we have 2 outcomes from the first and 2 outcomes from the second, which gives us 4 outcomes. So let's look at if we make it a bit trickier, because I suppose heads have just got 2 outcomes, which does make it easier. So what if I asked you to list all the events when we toss 2 dice? Now, that's a little bit trickier because if we use that fundamental principle of counting for a second, we know that there's going to be 6 outcomes on the first die and 6 outcomes on the second die, which means there's going to be a total of 6 by 6, so 36 outcomes if we use that fundamental principle of counting to figure that through. So problem with trying to list 36 outcomes is it's going to be tedious, it's going to be long, and we're prone to error. How do we make sure we have them all? How do you make sure you don't double count something? So we need to be a little bit more strategic or systematic in how we approach that. So what I mean by the word systematic is that we have a system in place. We're not just doing it randomly, we're doing it in a process that makes sense and makes it easier for us. So here is a way that we could work it, and it's called a two-way table. And this is what it looks like. We have a table. It has 6 rows and 6 columns plus headings. And what we have are the outcomes of the die across the top and the outcomes of the second die down the side. 1, 1 means I rolled a 1 and then a 1. Now, you could also say this could be quite tedious to write, yes. However, it would be very hard to miss an outcome doing it this way. So as you can see with the table, we have a 6 by 6 table, which actually helps us to understand a little bit better how that fundamental principle of counting works. Now we'll see it again with our probability tree, but here we can see, okay, well there's 6 across and 6 down, so 6 by 6, so there's 36 different things that can happen. So there are 36 different outcomes. Now you might look at this table and say it would be easier without the table, but often when we're working with 2 events like rolling 2 dice, we might have to do something with the numbers, such as total them, or even maybe multiply them. So now let's look at if I have a die and a coin. So what's the probability of getting a heads and a 3 when we roll a dice and roll a die and toss a coin? Now we could use the and is multiply here and it would work perfectly. However, if this were a question that already had the table, we could use the table. So let's look at what the table would look like and use that to help us. So this is what our two-way table would look like. It doesn't matter which goes where. So for example, I've heads and tails at the top. You could have those at the side. There'd be no difference. And again, you can see I have 2 across the top, 6 down the side. 2 times 6, there are 12 outcomes. So if we think of a heads and a 3, in my table, there's only one of those out of the 12 possible outcomes, which gives us an answer of 1 over 12. So you can see how quick and easy this is if we had the table. So I would suggest to use the table when we have a table, and often the questions we've seen in the past for the junior certificate have had tables there. But if there is no tables, you can go back to your shortcut of and is multiply or is add. So what's the probability of getting a tails and an even number when we roll a die and toss a coin? So let's go back to the same table and let's figure out everywhere we have tails and an even number. So we have tails in 2, tails in 4, and tails in 6. So that's 3 out of the 12 outcomes, but we always give our answer in the simplest form, so that simplifies down to 1 over 4. So let's look at what would happen if we were playing, for example, a game of Monopoly or another game where you roll 2 dice and add the scores. So here I'm making a little two-way table. I have a little plus in the top corners. That had been blank up to now. That plus is indicating that we are getting our answer by adding the numbers together. So let's fill in our table and it looks something like this. So when you play Monopoly or when you play a game that you roll 2 dice, it's important to understand that actually not all outcomes will be equally likely, because there are some numbers that are easier to get. So if you look at our table here, you'll see that our table has a lot of 7s. It actually has 6 7s. So there are a lot of different ways that your dice can add to 7. So you could get 6 and 1, 5 and 2, 4 and 3, and then all those ways reversed. So that's the most common number when we roll two dice and add their totals. So the numbers that are less common would be 2, because there's only one way to get that, a 1 and a 1, and 12. So there's only 1, 6 and 6. So there's only one way to get that. So this helps us get a better idea of a question that's more complicated. Here, and or is not going to be able to help us. So what number appears the most? And it's 7. And the next time you're playing a game, keep an eye out for that. Is 7 coming up more than maybe other numbers? So what numbers appear the least? Well, 2 and 12. So let's look at more questions. So what's the probability then of scoring a 7? Now, if we didn't have that table, This would be a really difficult question to answer because you'd have to look at all the different ways it could happen. You'd also need to make sure that you didn't leave anything out. So the easier way to do this would be to draw out this two-way table. So in my table, there are 6 different ways to get a 7. That is 6 out of the 36 outcomes that we have. And again, we always simplify down, so that gives us 1 in 6. So what's the probability of scoring a 5? Okay, so we go to our table. Our table, we have 1, 2, 3, 4 different 5s. 4 out of 36 total outcomes. And again, we always simplify our answer, which is 1 in 9. So final one, what's the probability of scoring less than 5? So again, quite a complicated little question if we didn't have the two-way table. So any numbers that are less than 5 on our table, we have a 2, we have a 3, and we have a 4. And we have a few 3s, we have a few 4s, but we've only one 2. So I have 1, 2, 3, 4, 5, 6 out of 36. And again, we simplify that to 1 in 6. Now let's look at an exam question that uses a two-way table. Paul is raising money for a charity in his school. He organises a fun day where one of the games is played using the spinners and the rules shown. Here's spinner A. It has 1, 2, and 3. Spinner B has 1, 2, 3, 4, and 5. The rules are you pay €1 to play the game, i.e. spin both spinners. Get the same number on both spinners, you get €1 back. And get a sum of 8 on the 2 spinners, you get €8 back. So complete the two-way table, show the sum of the numbers on the 2 spinners. So let's complete that table. So 1 and 1 we get 2. 1 and 2 we get 3. 1 and 3 we get 4. 2 and 1 we get 2. 2 and 2 we get 4. 2 and 3 we get 5. It's already in our table. 3 and 1 is 4. 3 and 2 is 5. 3 and 3 is 6. 4 and 1 is 5. 4 and 2, 6. 4 and 3 is 7. 5 and 1 is 6. 7, and finally we get 8. So that's our two-way table. Now there are more questions on this and we're going to return to them after we've reviewed some other material.
So now let's look at question 1 from the 2024 Junior Cycle Higher Level paper. Bia has 8 numbered counters. There are 4 red counters numbered 1 to 4 and 4 blue counters numbered 7 to 10, and we can see them directly underneath. She picks 1 red counter at random and 1 blue counter at random. Complete the table to show the 16 different pairs of counters Bia could pick, one of which is already done for you. So it's really important that we follow the same format that they've used. So we can see the one they filled in. They filled in the red counter, so from the left and then from the blue. So we're going to do that in that order, red and then blue. So this gives us 1 and 7. Here we get 2 and 7, 3 and 7, and 4 and 7. So completing this two-way table, the 1 and 8, 2 and 8 is already done for us. 3 and 8, and 4 and 8. 1 and 9, 2 and 9, 3 and 9, 4 and 9, and then 1 and 10, 2 and 10, 3 and 10, and 4 and 10. So the only thing to take care with these kind of two-way tables is make sure you're working through in the right order. So find the probability that one of the counters via picks is a 7. So let's take a look at everywhere where we see a 7 in this table. So there's 1, 2, 3, 4. And we can see here we have 16 outcomes in total. So that's going to give us 4 out of 16, or a 1 in 4 chance. Make sure any answers you give are in the simplest form. Then it says list the pairs of counters where both numbers are prime. This is not probability, but while we're working on the question, we should look at it. So let's take a look at our original and mark off which numbers are prime. So 1 is not a prime number. A prime number is a number which has only 2 factors. So what that means is 1 doesn't have 2 factors, it only has 1, it only has itself. So the first prime number is actually 2, and then 3. 4 is not prime, it is a composite number, it can be broken into 2 by 2. 7 is prime, 8 is not, 9 is not prime. So just be careful not to mix up prime with odd. 9 is odd, but it's not prime because it can be broken down into 3 by 3, and 10 is not. So what we're looking for here are any of our outcomes that contain a 2, a 3, or a 7. So I'm just going to change up my color. So we're looking for anywhere where there's a 2. So it's this whole line here, a 3, or a 7. So that we can easily count up. Sorry, it says list the pair. So we want to list where both of them are prime. So you would list everything there that we've highlighted in blue. Now let's look at question 2 from the Junior Cycle Higher Level 2022 paper. When Maeve's team play a match, they can win, draw or lose. Fill in the table below to show the 9 possible outcomes when Maeve's team play 2 matches. 1 is already done for you. WD means they win match 1 and draw match 2. The order here is really, really important, so do take care. So here we have win-win. Here we have drawing on match 1, winning on match 2. And we can continue this. So we get draw and draw, here we get lose and draw. Here we get win and lose, here we get draw and lose and lose and lose. So Maeve thinks that the outcome of each outcome in the table is equally likely. Based on this, find the probability that Maeve's team play 2 matches, they win at least 1 match. So what that means is we want to find all the outcomes where they win at least 1 match, which means they can win 1 or 2. So anywhere we find a W. So here we can see that there are 5 out of the 9 total. So part C is going to bring in a little bit of that and or we've discussed. So Maeve's team play 5 matches in a competition. Work out the total number of different possible outcomes for Maeve's team for these 5 matches. For example, one possible outcome will be WWLDW. Okay, so they can win, win, lose, draw, win. Now, what we've done in part A is we've used our two-way table to look at 2 matches. Unfortunately, given the fact that your screen or your page is 2-dimensional, we can't go beyond a two-way table. So if we want to go beyond that, we need to think of other ways we can work. So to figure out how many outcomes there are, we need to think about that there are 5 matches. So 1, 2, 3, 4, 5. Each match has 2 possible outcomes. So in the first match, 3 possible outcomes because we have win, draw, or lose. So in the first match, we have 3 outcomes. And multiply. The next match, we have 3 outcomes, and so on. So we continue this for each of the 5 matches. Now, if we were to simplify that, that's going to give us a 3 to the power of 5. So if you think about what this would mean in part A, we have 3 outcomes for match 1, 3 outcomes for match 2. There are 9 in total. That will be 3 by 3. So for us here, there's actually 243 total outcomes if they play 5 matches. Now let's look at probability tree diagrams. A probability tree diagram shows all the possible outcomes of 2 or more events happening, and it shows these by using paths or what we call branches, which we follow through. And there's 2 really important points to note when we're dealing with probability tree diagrams. The first is that all branches from a single point must add to 1. They must be exhaustive. And the second is to find the final probability, we must multiply the probability of each branch together. We're using the idea of the word and we'll see that as we work through an example. So here's an example of a probability tree diagram we can use. So in order to start a board game, a player must roll 2 6s in a row. What is the probability of rolling these 2 6s? So when we're working with probability tree diagram, we don't want so many branches that it gets confusing. So rather than deal with a branch for each number on the die, what we're going to do is we're going to break this into 2 options. The player will either get a 6 or not get a 6. So this is what we have in roll 1. They can get a 6 or they get a not 6. So our probabilities are going to be written on our branches here. So there's a 1 in 6 chance of rolling a 6 and a 5 in 6 chance of rolling not a 6. So basically any other number on the die. Then we do a second roll. So the second roll means that after each of our first roll options, we create new branches. So for roll 2, it looks like this. Again, we can see in the first roll we could get a 6, and then in the second roll we could get a 6 or a not 6. And if on the first roll we didn't get a 6, then in the second roll we could still get a 6 or not a 6. The probabilities are going to stay the same here. That doesn't have to happen. They can change. So our final outcomes are going to be maybe you get a 6 and a 6 and not a 6, not a 6 and a 6, and a not 6 and a not 6. And what we can see here is that there's one outcome which is the favorable one, the one that we want, and that's the one of rolling 2 6s. But be careful, just because there's 4 outcomes doesn't mean each of them are equally likely. They're actually not. So we're going to work out the probability of each of these possible outcomes. So what you're going to do is you're going to follow through on our branches to get to your outcome. So we follow through for the first one. We roll a 6 and we roll a 6 again. What that means for us is we roll a 6, so we have a 1 in 6 chance, and we roll a 6 again, another 1 in 6 chance. So our probability is going to be 1 over 6, and so multiplied by 1 over 6, which will give us our outcome here. So this probability will be 1 over 36. If we then think about, well, what about the probability of rolling a 6 and then not a 6? Again, we follow our branches. We follow through to here. We have the probability of getting a 6 and the probability of not getting a 6. So this will give us a 1 in 6 chance multiplied by a 5 in 6 chance. And we will continue that for our other two outcomes. A way to check that everything is being done correctly is to add those probabilities in red. And they should add up to 1. This should be exhaustive. So the answer here, in order to start a board game, what's the probability of rolling 2 6s? Our answer is here. So it's a 1 in 6 chance. Now, you may feel like a probability tree diagram is a little bit too much for that question, and there are other ways we can do it. We can do it with a simple and statement. We could have done it with a two-way table. However, there are questions where you won't have a choice, where you will have to use a probability tree diagram because the question forces you to, or because there's more than 2 events, so you can't use a two-way table, or sometimes it's just easier because the probabilities will change depending on what happens. Let's take a look at the 2019 paper 2 question 9, and here we can see that we're working with a probability tree diagram. This probability tree has been drawn out for us, and we can see that it's partially completed. On the right hand side, the question explains that Jerk flips a coin 3 times. Each time he can get a heads or tails. The diagram and the table below show how he can get each of the 8 different outcomes. Complete the table by doing each of the following. Write in each of the missing letters H or T on the diagram. Write the 5 missing outcomes and write the number of heads in each outcome. Okay, so let's start by filling in our H or T. So far we can see, if I just track through, we have heads, 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 tails. So we could fill in this outcome here. So this is heads, heads, tails, and there's 2 heads there. Then we can do heads, tails, heads, and that's filled in fully. Then heads, tails, and a blank. So if this one is heads, this one here must be tails. And that gives us an outcome of HTT, which has 1 head in it. And then we move down to getting tails first. So tails, heads, blank. So in order to understand what goes there, we look at the other part of our branch. It is T, so then we put a H in there. And that gives us our THH, and the number of H's are going to just be 2. So then we have tails, heads, tails. So what goes in here is THT, and that, THT, and that gives us one head. And then this one's the trickiest one to fill in. We have tails and then blank. Here we've heads, so this one must be tails. And then how the third flip has gone in each, it goes heads, tails, heads, tails, heads, tails. Technically, the order doesn't really matter, but we'll follow through the same order. So that's heads and tails. Following these pathways, we get tails, tails, heads. So TTH, and that has one heads. And then we have TTT, which has no heads. So that's our diagram completed. So then they ask us if each outcome is equally likely, fill in the table below to show the probability that juror gets each of the given number of heads. So for us here, how many ways or how many different outcomes had 0 heads? So there is actually only one. I'll just use a highlighter so we can see it. So this is the only one, and that is out of 8 total. So we have a 1 in 8 chance of getting 0 heads. Okay, and then if we look at 1, so let's see where we can see getting 1 head. So we have here 2, 3, so there's 3, and again they want the probability, so it's going to be 3 out of 8. For 2 there's another 3 out of 8, and then for 3 there's a 1 out of 8. And again, a quick check is always what happens when you add those. We get 8 out of 8, which is 1. They're exhaustive, so that's correct. We should have you should be getting one of these probabilities. So looking at adding them all together, what we're saying is you should get one of those outcomes, so heads, 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 or heads, heads, tails, etc. And that means they're exhaustive. They should all add to 1. So the rest of this question, it isn't related to our tree diagram, but it is nice to see what's going on. So Fidelma flips a coin 8 times. Now, we could draw a tree for this, but that's going to get quite big and quite messy. So instead, we're going to focus on using our and our or statements. So write down the number of outcomes that have no heads. So we have 8 coin flips. So that means the only one that will have no heads is the one that's all tails. So tails, 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 tails. So we have 8 tails. Sorry, 8 tails. So the number of outcomes with no heads, there's actually only 1. So work out the number of outcomes that have exactly 1 head. So then if you take what we had, we can move 1, 2, 3, 4, 5, 6, 7. We can effectively just keep moving the H into all the different positions. Now it's absolutely fine if you want to write all these out. In an exam, you, I suppose, may not have the time, but it may give you kind of peace of mind to do this. 1, 3, 4. Okay, and then we can keep going. Now, you might at this point have already figured out there is a kind of a quicker way. Once you've figured you can keep moving the H, that there is a quicker way to figure this out. So we're nearly there. I'll keep going. 3, 4, 5, 6. H and T, and then last one, T, 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 H. And we can see that there are 8 because there's 8 different positions that that one head can get into. So here we could have just gone straight to 8. You didn't need to draw it out. However, it's nice to kind of see how we could draw it out if we needed to. So then work out the total number of outcomes when Fidelma flips a coin 8 times. So anytime we want our outcomes, we're thinking about that fundamental principle of counting. 6, 7, 8. So we do 8 times. For every flip, there's 2 outcomes. So heads or tails. And then the second flip, heads or tails. Second flip, and so on. Because that word and, we're multiplying. Simplifying that, one more. Simplifying that gives us 2 to the power of 8. So you're multiplying 2 by itself 8 times. and that gives us 256 different outcomes. So now let's explore expected frequency. So the expected frequency is the frequency. So remember, the word frequency just means how many times an outcome is expected based on the probability of that outcome. This is something that's quite intuitive, but as the questions get tougher, it can be hard to then apply what you would do to kind of a number question. So let's start off with something really simple. So if I roll a die 120 times, how many times would I expect to get a 5? So the first thing we do is we think about, well, what is the probability of getting a 5? So there's 1 5 on the dice out of 6. So we would have a 1 in 6 chance of rolling a 5. But another way to think about it is 1/6 of the time we will get a 5. So that means 1/6 of 120. And that would give us our 20 times. Now, that is basically what we're working with. We're saying the probability of that outcome multiplied by the number of times we do something, or the number of trials. So we already saw the start of this question. It's question 2 from the 2016 paper 2 junior cert higher level paper. And we already did part A earlier in the video. So I've just pulled that through. And now we're going to look at part B and part C. So just as a reminder, Paul is raising money for charity in his school. He organizes a fun day where one of the games is using spinners, and the rules are shown below. So the first thing we did was we completed our two-way table to show the sum. So when we're adding together the two numbers on the spinners. Now the rules are you pay €1 to play, and then if you get the same number on both spinners, you get your €1 back. And if you get a sum of 8 on two spinners, you get €8 back. So what we're being asked in part B is find the probability that you get €8 back if you play the game once. So the way we get it back is if there's a sum of 8. There's only one way that this can happen. So the probability of getting €8 back is 1 out of 15. So that's our probability of getting our €8 back. So then in part C, it tells us 320 students play the game. Find out the number of students you would expect to get €1 back. So we need to, first of all, think of, well, what's the probability of getting €1 back? So you get €1 back if you get the same number on both spinners. So the only way that could happen would be getting 1 and 1, 2 and 2, and 3 and 3. So these are the three ways that it can happen. So that is 3 out of 15, or simplifying that down, a 1 in 5 chance. So there's a 1 in 5 chance of getting €1 back, which means 1/5 of the time we would expect a student to get a euro back. So 1/5 of 320, and that would give us our 64 students. So that is how we would work with that expected frequency. You may not see those words. It will be asking you something about expecting. What would we expect to happen? So the final topic we're going to look at in this video is relative frequency, which is also known as experimental probability. And the idea here is that sometimes it's too simplistic to simply say just because there are three outcomes, each outcome is equally likely. So, for example, if you were playing a match, you could win, lose, or draw. But both of those, well, three of those options, they're not all going to have equal probabilities of happening. It's not a 1 in 3 chance. You would have to look at factors like how good is your team? How good is the other team? Is there something that might affect it, like are you home or away? Is the weather going to play a part? So there's a lot to take into account. So in this part, in this kind of experimental probability section, what we're looking at is how to figure out probabilities based on past events, based on what has happened in the past. So, for example, we may need to take into account emotion or pressure. So, think about taking free throws or a penalty taker in a football match. So, what we're going to work on now is a scenario where the probability is not theoretical. It's not something we can figure out mathematically from how many outcomes there are, but instead we're going to look at what has happened in the past. So, thinking in terms of an experiment. So, a penalty taker for a soccer team took 25 penalties during a season and scored 20 of them. So, what's the relative frequency of scoring a penalty? So, what we're being asked is based on what's happened in the past, what is the probability that he will score a penalty in the future? That's what we mean by this relative frequency. So, he got 20 out of 25, which is going to then simplify down to 4 over 5. So when the same player takes 10 penalties next season, how many do we expect him to score? So we'd expect him to score 4/5 of that 10, which will be to score 8 in total. So then it asks us to discuss a weakness in this system. So obviously using the past to predict the future is not perfect, but often it's the best that we have. This is what a lot of sports teams will use when we're trying to figure out what the probability of somebody making a free throw, somebody making a penalty, somebody winning a match, anything like that, because the best information we have is the past. But just because this has happened in the past doesn't mean it will happen in the future. So, for example, we were told here in this question that they took 25 penalties and scored 20 of them. Maybe it was a particularly good year. Maybe they were playing very well. Maybe that was a particularly poor season for them. Maybe they could do much better. So, we're basing our prediction for this year on last year, and they may not align. So let's take a look at question 4 from the 2014 Junior Cert Higher Level Paper 2. In an experiment, a standard die is tossed 600 times and the results are partially recorded in the table below. Calculate the number of times that the 5 appears. So the first thing we're going to do is we're going to add together all the current frequencies that we have. Plus 98 plus 105. So when we add these together, we get 511. We know that there was 600 in total, so we take away our 511, and that's going to give us 89. So 89 is the frequency that's missing above. After looking at the results, Anne claims that the die is unbiased, so it's fair. Do you agree with her? So it was tossed 600 times, so we would expect, so 1/6 of 600, we would expect that each of the numbers comes up about 100 times. Now, what they're really looking for you here is to understand that we're expecting them to come up 100 times. You may feel like they are pretty close and this is a fair die. However, it's unlikely that it's fair given this particular result and this result. They're quite different. So, based on that, we would probably say no. We expect each number to appear 100 times. Now, here's the thing. You're not going to get exactly 100 all the time. But 3 and 5 are quite different. They're different enough for us to kind of challenge this being fair. You could argue to say, well, 92 is also a little bit fair, 105, but these two in particular are the ones that would cause us concern. So let's take a look at question 8 from the 2012 Junior Certificate Paper 2. What's the probability of getting a 1 when a fair dice is thrown? So there's 1 out of 6. So that's a nice straightforward question. So a fair die is tossed 500 times and the results are partially recorded. Calculate the number of times a 3 appeared. So let's add together the frequencies that we already know. And when we do that, we're going to be able to compare our answer to 500. So when we add those together, we get 414. So we know that there's 500 in total minus that 414, and that gives us 86, which goes into this section here. So part C asks us to calculate the relative frequency of each outcome and write it in the table above. Give your answer correct to 2 decimal places. So let me pull in the table. And the relative frequency, what we're going to do, I'll just pull it out here. We're going to put the frequency, so in this case 70, over the total number of tosses, which gives us 7 over 50, or 0.14. So that one is a nice decimal that doesn't need to be rounded. The other ones might. So we're going to do this for all of our numbers. So for 2, it's 82 out of 500. So that is 0.164, which is just going to round to 16. Then we get 86 divided by 500, and that gives us 0.17. And then we get 90 divided by 500. That gives us 0.18. 91 divided by 500. And that gives us 0.182. We round that to 0.18. And finally, we get 81 divided by 500. And that gives us 0.16. And then the final part of this question, part D, give a possible reason for the difference in value between the relative frequency of 1 in the table and your answer for part A. So remember our answer from part A, the probability of getting a 1 is a 1 in 6 chance. So if we then convert that to a decimal, that gives us 0.16 recurring, and rounded that gives us 0.17. So we have 0.17 from part A, so that's from part A, versus 0.14 from part C. So one reason for the difference in value is possibly this die is not fair. Possibly it is not a fair die. They're not evenly, each outcome is not equally likely. But equally, it may be a fair die and we just haven't got those answers. Sometimes in experiments, we're not going to get perfectly theoretical answers. You might argue that they're close enough. You might argue that they're not. Really, they want you to understand, or they want you to demonstrate that you understand the difference between relative frequency, which is using actual data, actual experimental data, versus our theoretical answer from part A.